three presenters that will go through basics of MRI, security of MRI, and maintenance of such devices. The first one will be Jim Zapput from GE Healthcare, and following we have Edna Marina de Souza and Li Bing, who will be with us with a recorded speech, being late at night in Shanghai where he lives. So I will give the floor to Jim right away. So he will present his presentation on the introduction and differences between MRI system, more or less the basics of MRIs. He's been working in the MRI field for over 20 years, and he has both a technical and a sales perspective, and also a formation and teaching courses perspective. So I think that we have the whole idea of the system. Jim, just go ahead. Floor is yours.
Thank you, Umberto. Appreciate the invitation. Thank you for having me. So as Umberto shared, I've got a very long relationship with the modality of MRI that this group has asked me to share, or try to share, in 15 minutes. So 37 years of MR in 15 minutes. I'm going to apply my New York 15 minutes and try to get you there. Next slide, please. What we're going to try to cover is, what is MRI? What are MRI's inherent hazards? We're going to talk about magnets, superconductors, and cryogens, and the imaging system components beyond the magnet, right? There's a whole system. Once you get past the magnetism in the MRI and the magnet, it begins to look a lot like other traditional modalities. So here we go. Next slide, please. First, what is it and why? MR is the only diagnostic imaging modality where the patient tissue is the source of the image data. Comparing to other modalities, X-ray, CT, vascular, mammography, these are all based on an X-ray source, attenuated through tissue, and the shadow is detected. Right? When we consider nuclear medicine and PET, these sciences apply radioactive isotopes that are tagged to metabolites, and these isotopes follow along for the ride to the tissues of interest, and it's that radioisotope decay that is detected. Ultrasound is based on acoustic waves of a propagating frequency reflecting off tissues and structures, and that reflection off those tissues is what is detected and the image created. MR is profoundly different. Let's take a look at how. Next slide, please. So how is it different? MRI depends on the efficient absorption and return of RF energy at a patient's tissue resonant frequency, 63.86 megahertz for 1.5 Tesla systems and 127.72 megahertz at 3T systems. This resonance is very analogous to a child on a swing in the playground. If you impart energy to that resonance system at the right frequency, meaning push the child at the right time, that system, that mechanical system, will efficiently absorb that energy and return that energy, lessening, of course, friction losses at the pivot point and air resistance. But it's an efficient absorption and return of energy. MRI also depends on the abundance of water in the human body. When we're talking about taking an MRI image, we're talking about imaging water, thus making MR ideal for soft tissues and ineffective for bone imaging. Interestingly enough, I was part of a talk earlier this week where I learned that bone imaging is no longer a challenge. I was introduced by Dr. Potter at the Hospital of Special Surgery, and if you can imagine the life of an orthopedic surgeon, there are implant angles that have to be known. And prior to the work that she's done, you're required to get a CAT scan of the joint area in order to calculate these surgical angles. She considered the challenge of, what if I could get those same angles with MR? It's certainly not a traditional CT image, but it is a sufficient image to get those bone angles so surgeons are not asking their patients to have a pre-CAT scan and incur that radiation. Very, very exciting stuff. Back to the pitch. The singular purpose of the main magnetic field is to polarize and align the patient's hydrogen protons to parallel and anti-parallel orientation. Only 1 in 1 million hydrogen nuclei contribute to the MR image, and of those, only a small fraction are actively producing MR image detail. Next, please. So let's talk a little bit about the evolution of the main magnetic field. The original MRs were resistive magnets, meaning they were wound out of coils of conventional resistive copper wire or some copper alloy. These are energy intensive, they are heat producing, they are inherently unstable, right? Imagine trying to keep current control in a large resistive magnet as temperatures change during operation. This limits them to low to moderate field strength at human imaging volumes, typically less than a half a Tesla. Silver wire has been used in scientific magnet applications because of its much lower resistance, but it's not practical for imaging use. The scientific application of silver was the Manhattan Project. Permanent magnets, right? These are naturally occurring rare earth materials. Zero energy to operate, but they're sensitive to magnetic material temperature variations. So we insulate them very well. We put thermal control systems on them. These are also limited to low to moderate field strengths at human imaging volumes. These will tend to come in at less than 1 T. As this engineering does not require a solenoid of wire, this is what makes possible the open or the large gap product geometries. So all of the open MRIs that you recall for larger patients, larger body habitus, these were based on permanent magnets. Fast forward to today, the superconductor. These are coils of zero resistance wire at an ultra low temperature. This is currently the state of the art of MR across all of the major OEMs. Minimal energy to operate, right? Because the operation is limited to only the cold head and the thermal support systems. Inherently rock solid magnetic field stability. 1.5 T and 3 T at human imaging volumes are now common. 7 T is the next frontier now being explored. That rock solid main field stability comes from Mr. Maxwell and Mr. Lorenz's equations that say once you've defined the geometry of a magnet, of a solenoid, and you've defined what the current is in that solenoid, those two being constant, the resultant magnetic field is a constant. These are, however, sensitive to environmental vibrations and electromagnetic interference, so pre-sighting qualification work is critical. These also store massive amounts of energy, requiring direct venting to outside. These magnets are always on and silent, regardless of the local electrical state of observable systems. This is important in a situation as Hurricane Ian down in Florida, right? Imagine all of those hospitals that are blacked out, flooded. The superconductive magnet stays on. It remains energized, even though everything else about the hospital appears to be powered off. Next slide, please. So the biggest difference, literally, is a superconducting magnet, right? We still have a patient table. We still have to put the patient in the middle. We still have an enclosure. As technology is advanced and the MR magnets themselves have gotten shorter front to back, right? We want to address patient comfort. We want to address claustrophobia. Try to get the tube to be as short as possible. What you'll start to find is MRIs have become almost the size of large PET CTs. They can be indistinguishable dimensionally. So things have improved, but the magnet is different. Next, please. So let's take a look inside at superconducting physics. When we say the magnet, or you see an MRI in a suite, inside that magnet, there are usually 8 coils. There are 6 main field coils and 2 shielding coils of superconducting niobium titanium wire, several miles of which are all in series. When that structure is cooled to its critical temperature of 4.2 Kelvin and held there by an immersion in liquid helium, the 750 amps of main field current flows with 0.0 ohms of resistance. Nothing, not a fraction of an ohm. It is superconductive. What you can't escape, though, is the massive inductance, greater than 20 henries on an air core. Next slide, please. Let's touch on the first 3 hazards of MR, right? We talked about the stored energy. The physicists look at the superconducting magnet as a pure energy storage device. At imaging fields, where we scan patients, the amount of energy stored in a typical MR can be anywhere between 3 and 10 million joules in the magnetic field. This creates a translational force, across ferrous metal objects near an energized magnet that will place a force on it often beyond a human's ability to counter it. The object will travel, its path will be unpredictable, and it will injure persons and damage equipment along its path. For this reason, all approach assumptions must be that the magnet is always on until you've proven that it's not. Very much like Lotto, very much like other safe work procedures, you have to assume the magnet is on unless it's been proven otherwise. Stored energy, if released into the liquid helium bath, is called a quench. The word quench we borrowed from metallurgy. It simply represents a large change in temperature over a very short period of time. You know, they'll harden metals by taking a hot piece of metal, putting it in a bucket of oil to change the temperature from hot to cold very rapidly. That's the definition of the word. It can be purposefully initiated in response to an accident. So the operator of the scanner has the ability to turn the magnet off. If there is a life safety incident, I'm sure Dr. D'Souza will have more about that later, so I won't get into it here. But the operator does have the ability to turn off the magnet if a patient's or another person's safety is impacted. Turning off the magnet is not a reason. You shouldn't have to turn the magnet off for non-human related accidents. If a bucket or a tool or a machine or a table is attracted to the magnet, becomes stuck, that's not a reason to quench the magnet. Close the door, call your service provider, and there is a better way to respond. But if there's a person involved, if there's human injury involved, don't think twice, immediately quench the magnet, turn the field off, and respond to the crisis. And lastly, the resultant helium. So we have the energy that is stored in the magnet, is absorbed by the liquid helium. That liquid helium converts to a gas, and that gas has to be vented out of the room. By engineering design, that helium is routed up to a quench pipe, obviously, and is ducted outside the building. Helium is not reactive. It is not poisonous. The primary hazard of helium gas is that it displaces oxygen. Helium gas is a simple asphyxiant. And third, cryogenic temperatures. During service events or following quench events, metal surfaces on the magnet and support plumbing can become extremely cold, sufficiently cold to cause frostbite on contact. Next, please. So getting beyond the magnet, right? What drives MR performance? The gradient amplifiers drive scanner performance. You can have a Datsun 4-cylinder on the left. You can have an Audi R8 10-cylinder turbocharged V10 on the right. That is what differentiates scanner performance, is gradient performance. Shown here are the amplifiers. Obviously, there's a gradient coil that has to receive that energy without destroying itself. That's the other half of the equation. Next, please. RF coils, think of these as antennas. This allows us to communicate with the patient, give them resonant energy, and listen for the signal in return. Next, please. RF amplifiers carry the image excitation to the patient, right? It's the RF transmitter. Again, they scale with field strength. 1.5 is smaller, 16 kilowatts. 3T is about 30 kilowatts of peak transmitted RF power at those frequencies. Next, please. So as a clinical operations group, you either worry yourself or you want to know what your service provider is giving you for that magnet maintenance and cryogen contract. It has become all magnet maintenance in recent years, last decade. In a world that doesn't have an infinite supply of helium, in a product installed base that is by and large part zero boil off, does not consume helium on normal operation, what are you worried about? What does a service provider worry about? We worry about preservation of helium, conservation of helium. We all, and vendor agnostic, we all watch magnet performance very closely. We act on trouble before it occurs. We detect problems before they cause issue, and we correct them before helium is wasted. That is the name of the game in today's helium market. Next, please. And very briefly, you'll see these a common departmental precaution is a carpet in front of the screen room door that simply warns anybody on approach there is a powerful magnet that's always on, do not enter. So with that, I'd like to pass it over to Dr. D'Souza to get a little bit deeper into safety aspects of MR.
Thank you, Jim. So we hand over the stage to Edna Marina D'Souza. Sorry for my mispronunciation, although I should speak a little bit better Spanish or Portuguese rather than English. Edna is a medical physicist at the Biomedical Engineering Center of the State University of Campinas, and she has deep knowledge in magnetic resonance security and other issues regarding MRI safety. So go ahead. Thanks.
Thank you, Humberto. Hello, everyone. It's a pleasure to be here and talk a little about MRI safety aspects. I would like to take the invitation of the Global Clinical Engineering Alliance to participate of this event. Next, please. So here we have a picture of the State University of Campinas, Unicamp, showing the extension of our university. Next, please. And here another picture highlighting the Center for Biomedical Engineering near the clinical hospital of Unicamp. Next, please. MRI is a medical imaging technique based on high-intensity magnetic fields gradients, and radio frequency pulses, as previously discussed. The method allows the generation of images with different types, such as structural, functional, water diffusion-based, and others, providing different information about the human body in health and pathological conditions, especially when we consider the soft tissues of the body. And here we have some examples of these images, right? Next, please. Here we have other examples of 3D MRI reconstructions of brain, kidneys, and heart, showing the high level of details of the structures reconstructed. Next, please. So, what are the possible effects of the interactions of high-intensity magnetic fields and their gradients and radio frequency pulses with human body tissues and medical devices? Well, in medical devices, the magnetic fields can essentially induce electrical currents, which can be a risk for patients and the device's integrity, especially considering the devices incompatible with the MRI environment. According to FDA, for fields until 18T, there is no significant risk for adults. For 9.4T, we can observe some sensory responses. But nowadays, there are many studies evaluating cell growth patterns, DNA integrity, and other physiological parameters. But until now, there are no adverse effects that justify a great restriction of MRI use. Next, please. Radio frequency pulses have many applications in medicine, for example, as in tumor ablation, skin or brain treatments, and in MRI. Most of the effects of these pulses occurs because of the molecular excitement caused and heating of tissues. Most of the transmitted power is converted to heat, and we can estimate in MRI the power deposited in tissues using the SAR parameter. However, the radio frequency dosimetry is non-trivial because it depends on protocol parameters and many body measurements. Next, please. Finally, magnetic field gradients can induce electrical currents in the body and also in medical devices. It can lead to stimulation of muscles and nerves, for example. These currents can also compromise the operation of many kinds of medical devices. Next, please. Considering the medical devices and the MRI environment, it's important to know how the behavior of medical device in presence of high-intensity magnetic fields, their gradients, and the radio frequency pulses. Here we have some examples of devices that can have dangerous interaction with MRI scanners, such as oxygen tanks, infusion pumps, and pacemakers. Next, please. For example, electrical currents induced by magnetic field gradients can compromise the operation of pacemakers, vital signal monitors, and infusion pumps. On the other side, orthopedic implants may generate magnetic field distortions, leading to imaging artifacts. In these cases, presented just in the interest region of the exam. It can compromise the detection of lesions and also the follow-up of the area with the implant. Next, please. In some cases, the patient may have body piercings, tattoos, and transdermal medicines, for example, which can lead to burns and skin injuries due to heating. Next, please. Here we have some types of MRI accidents reported. The most common of them is the missile effect, followed by heating and burning, and events of hypoxia. Next, please. In this case, a boy died because an oxygen tank hit his head, causing a trauma. However, nowadays there are aluminum-made oxygen tanks that can be used inside the MRI scanner's room to avoid this kind of accident. Next, please. This is another example of missile effect. In this case, the patient was hit in her face by a hospital bed made of ferromagnetic materials. However, nowadays there are also specific beds to transport patients safely to MRI's exam room. Next. In this case, again with oxygen tank, the patient companion was hit by the tank, which led to bladder rupture, a serious accident in India. Next, please. Now, let me give you an example of burning occurrence in MRI exam. In this case, a child was put inside an MRI scanner with a thermal blanket. Consequently, during the exam, the application of radiofrequency pulses excited his body molecules, leading to burn on his arm. This accident could have resulted in many severe burns in her body. Next, please. Other example of burn in MRI exam, but here due to chest electrodes forgotten on the chest patient. Next, please. In this case, a boy lost his finger due to burn lesions caused by an MRI exam conducted with a monitoring device over his thumb. Again, heating effect. Next, please. Finally, an example of that by hypoxia, because of the helium leaking inside MRI's exam room. Helium is the compound applied in the magnet refrigeration. In this case, the patient was not taken out of the room in time after a helium pressurization valve rupture. Unfortunately, she died. Next, please. So, what we can do to avoid this kind of accidents? First of all, training. All team must to know the safety rules for MRI exams. Classification of areas to identify potential risks in each place of an MRI service. Some hospitals also apply metal detectors to reduce the chance of the presence of ferromagnetic materials inside the exams room. Access restrictions of people that don't know the safety rules of MRI environment. And finally, an organized exams workflow. Next, please. Thank you very much for your attention, and I'm here for some questions that you have.
Thank you, Edna. You've been very fast, actually. You did have some more minutes to go, but we're fine by that. We'll keep them available for questions and answer at the end. As I was saying, our third virtual speaker in a webinar, which is kind of crazy, but we can do that, will be Li Bin, who is chairman of the Clinical Engineering Society of the Chinese Medical Association and has been working for more than 20 years as a trainee and as clinical engineering at the Shanghai Hospital. We have a recorded video, so I will ask Kali Roy to have it run, and so let's hear Li Bin's presentation.
Hello, I'm Li Bin. I'm glad to be here to share the presentation how to manage a MRI project in hospital. I'm Li Bin from China. I have been working in MR room in radiology department for 4 years, and have been for the GE company for MR service for more than 2 years, and also for the C department for more than 20 years. What we face challenge for the MR project? The system is so expensive and complex. It have a strong magnetic field, and also it's sensitive to variation of magnetic field, and sensitive to the IF radio frequency. And also the magnet is so heavy, it's superconducting, ultra low temperature, and also it's an integrated system and not stable enough. How to plan a magnetic resonance project? To complete the setup and operation of MRI system, the team of the multiple person is needed. And also the team people should include in the variety of the knowledge, including architecture experience, MR equipment experience, and the professional shielding design, and also the medical process and the medical supporting system knowledge. It should be included. There are 4 key stages of MR project. First one is site planning of the MR equipment room. First of all, we should select the MR site floor. For normal magnetic, is very heavy. It's about 5,000 kilograms to 10,000 kilograms. So MR system is generally installed on the first floor or the basement. But this year's the new magnetic development The liquid helium of free technology adopt so the magnet become the great reduced. So this new type of MR system can be installed on the higher floor with a special without special reinforcement or the loading. Second, we will consider the MR rooms, how big it should be. There are two types of MR systems room. One is without equipment room, together with the control room and the equipment room. There's a magnet room and a control room. Another type is with 3 room, magnet room, control room, and equipment room. This is the most popular design, and this should be considered. And each room has a minimum service area with requirement. The magnet room, control room, and equipment room has a minimum dimension size and a square area. It should be considered. Each MR system has a special requirement. And the MR system need a different room dimension. According to the menu for each product, there should be give the instruction. This is for 1.5 G's MR systems. Another thing we should be considered is avoid environment affecting the uniformity of the magnetic field. The variation of the environment will affect the uniformity of the magnetic field. The magnetic field interference have two kinds of results. And one is static interference, such as steel bars, steel in building. It can be generally overcome by the active or passive shielding. Another kind is dynamic interference. There are two types of dynamic interference. One is a moving ferromatic object like a wheel car, and another one is a device that generates alternating magnetic field, such as transformer. And this dynamic interference cannot be estimated and overcome by active or passive shielding in MRI installation. So we should consider other equipment maybe have a potential interaction with the MR systems. Here is the magnetic moving metal sensitive line plot. This information should be used to evaluate the potential site interaction with the MR equipment, such as trucks, bus, cars, and the 3 goals for all these one. And the truck and the car should be far away enough from the MR systems. This is the ISO Gauss plot show the ideal magnetic field relative to the magnetic isocenter. The car, the truck should be far away from this isolate line 1 and the line 2. The second key stage of MRI project is the installation of MRI equipment system. Primary magnetic field is too large. It should be needed magnetic shielding. There are 2 types of magnetic shielding. One is a passive shielding. Passive shielding should be one is construction of thick steel to enclose the magnetic room, like this one. Second is bolt the metal to the magnet itself. But now most manufacturers using this active shielding is using a secondary magnet as wrapped around the primary magnet to reverse external field. It can be reduced this metal to reduce the cost, reduce the room, But this kind of shielding is suspected to the moving metals like elevators, cars, trucks, and the train. So it needed to minimize the space outside. The medical equipment also needed to avoid being affected by the magnetic field. For example, the nuclear camera, which should be outside of the line 1, and the linear accelerate, cyclotron, accurate measure scale, analog image interference, bone dimension meters should be outside of this line 0.1 MT. And the most this equipment would be far away, affected by the Mri systems. And also this scanning room needed IF shielding. The amplitude of the Mri signal is very small and is very sensitive, easily interfected by the mHz radio waves from outside. To avoid external interference, it's necessary to isolate the magnetic resonance signals detection system from the outside world. The scanning room is often weighted with a thin copper sheet to form the RF shielding room. Like this one, this is a shielding for the penetration panel. The generally electromagnetic wave should be reach 90 to 100 dB. The door and the window with the scanning room need a spatial shielding. And also another should consider is the quench. In case of quench, liquid helium will instantly become high pressure helium. If helium diffused into the scanning room, it may cause experience of person in room. So we need to install the quench exhaust pipe must be installed outdoor and must be provided with fans and relevant sign to prevent the personnel from entry by mistake. It may be caused personally injured. The third stage of Mri project is management of Mri systems patient scanning. Safety for avoid the injured to the patient. These people with medical patches in the body, these people carry metals objects such as a watch, bracelet, necklace, and a coin cannot take the exam. This where the wear says, weight says, cannot take the exam. And also in the examination, avoid the formation of closed eye loop. Also, formation of closed loop vary between the eye coil cable and the ECG cable. It may be make injury for the patient. And also the safety that make the management of the entry scanning. The scan room entry should be fixed with a warning label. The label indicates the presence of a strong magnetic field, no entry of very magnetic material, personnel with cardiac, open flames of open substance, and also magnetic card, ferro fire extinguisher. If possible, maybe we can install the metal detection doors at the entry of the scanning room. That's avoid the patient or staff injured and the equipment injured. Damage. The magnetic field of Mri is very strong, very powerful, and never expired. and never underestimate the power of magnetic field. And also we need to precaution and maintenance for daily work. The MR system is a complex system. It's recommended to check and record working condition of the magnet, refrigerate, outdoors water cooler, and the temperature, humidity of magnet and equipment room at the beginning and end of the day. For example, for G systems, we should check all these meters. The fourth stage is a regular maintenance of MR systems. The MR system is an integrated system, which is not stable enough. It's needed preventive maintenance regularly. The maintenance items, including security items, system performance parameters, this is very important. And the general data checking, liquid helium level, magnetic pressures, and the various mechanical movement, whereas various linkage to the normal or whether the bed is moving smooth, and also including dust remove using recommendations. This is some checklist. According to the ACI Radiology Quality Control Manual, the quality control testing frequency is as follows. It needs 1 week or 1 month. And also the MRI image analysis with should be analysis with magnifying phantom, the QA with the magnifying phantom, scanning and setting like this one, and set the phantom at the positioning. The first, very important parameter should be setting to the signal to noise ratio. This is a very important parameters. Can be calculate this ROI status with the centers data. We calculate the signal to noise ratio SNI can be obtained by the following formulas. Second important is uniformity of the image, and we can calculate the 9 regional of data and collector with maximum and minus minimum, and to calculate this uniform. The third, the parameters is slide thickness. The maximum half width of the sensitive profile line is measured. The lower, the layer thickness Z is the image layer can be calculated using the formula as follows. And the fourth parameters is a spatial resolution. We can use the third level scanning phantom and use the vision to determine the maximum number of lines that can be resolved in the image. That is spatial resolution. The fifth parameter is the linearity of the image. We can measure the whole of space in X direction and in Y direction respectively, and compare with the measured actual distance and calculate the linear rate. We can get the linear rate as a formula. The sixth is a low construction resolution. We can use the vision to determine the image of the circle hole with the smallest dippers and the diameter that can be clearly distinguished. That is low contrast resolution. So make the conclusion of the management of MRI project. We always face this challenge. The key point is the required team, planning, and training. Suitably allocation of the MRI site, and the magnetic field shielding, IF shielding room, house loading, and the magnetic transportation, and also quench prevention cooling system maintenance, and regulatory maintenance. This is a key point for this MR project. That's all. Thank you.
Okay, we're finished with our presentation. So I would like to thank also Libin for his presentation, although recorded. We have spare time for questions and answers. A couple of those were already answered on the question and answer part of your Zoom application you have on your device. I will go rapidly through them. One was about having a metal detection room prior to get the patient inside the MRI room. This was addressed mainly to Edna Marina. So I would like Edna to answer the question, although then maybe Jim may add a little bit of other infos. Just go ahead.
Okay, thank you, Humberto. So yes, because with the metal detector, we can avoid the presence of some ferromagnetic materials inside the exams room, and also the presence of materials that can create imaging artifacts. But it's only one piece of security protocol. Okay.
So basically, we need to start security protocols in our MRI facility inside the hospital just to have all the pitfalls taken into account and figure out whether the ferromagnetic detection system, maybe on the door, as it was stated before, might be just end of the line issue, but you have to go through some checks before you do that.
Yes.
We had a couple of questions were more related to the device itself. There was one about the cautions to avoid loss of helium, especially in tropical environment, that goes together with another question that was regarding cooling and cooling opportunities just to maintain the cryogen cooling system available. And then there are two more questions I would still address to Jim. And one is the minimum distance of the transformer car parking from the MRI room. And another one that really is interesting and kind of tricky for me too. I saw it before. There was someone asking about the fact of having two MRI scans in the same room. There are more. Just go ahead with these, James, and there are more
Certainly.
questions coming up, and we'll keep them posted later.
Thanks, Humberto. The challenge of magnetic interference, whether it be from a vehicle or external sources, I think the writer mentioned transformers. It needs to be engineered for. There's no set distance. There's no set rule, because the magnetic field, both of the MRI and of the source of the interference, they are vector forces. They have a magnitude and a direction, and vector forces will add according to vector math. So the magnitude of the interference vector, the direction of the interference vector, all need to be understood. And very, very simply, the magnitude of the vector of current flowing in a cable can be calculated. So you would need to know the amps that are flowing in a circuit of a nearby conduit in order to calculate the potential interference. So it can be known, it can be measured, and it can be qualified for in pre-siting engineering studies before you commit to the site. What was the second question, Humberto? Two magnets in the same room.
Yeah.
They may not. You may not put two magnets in the same room in the same safe, controlled space, but you may site two magnets in two rooms that are within the same suite. So it's very common to have multiple MRIs in separate rooms, but occupy the MRI suite of 2, 3, 4, 8, provided those individual magnets are excluded from each other magnetically, and there are design considerations for that as well.
Yeah, there's one more question for you about shielding of the magnet, because Bean was saying that the passive shielding is not used anymore, or it will depend on the type of installation, or if there is active shielding
Correct.
available.
Predominantly, all current MRI OEMs, we all use active shielding, meaning there. And when you saw earlier my schematic drawing of a magnet, there are 6 main coils that produce the magnetic field, and there are 2 shielding coils. They work together to produce a vector sum in the bore where the patient is, and a vector cancellation outside of the magnet where the patient is not. So there are 2 vectors working against each other outside the magnet and working with each other inside the magnet. Passive shielding went by the wayside because of weight alone. We needed to site MRIs on higher floors of buildings, and the weight of the mass of passive shielding became unmanageable, and it's certainly almost impossible at 3T. It was fashionable for a time at 1.5, but completely impractical at 3.
Okay, there's one more question about the MRI functioning after shutting down the magnet. I'm quite sure that it can be done if the shutting down is done on purpose and with a well done procedure, because we did it in our facility to upgrade the system. I would ask the question to Jim about the fact after a quench, what we're going through. It's either we have to get rid of the MRI or we can still make it.
Sure. I have to apologize to the author. I misread the question. So, will an MRI continue to operate after it is shut down? I took that in the immediate sense, meaning, no, you can no longer image after the magnet is off for physical reasons. But once the quench is recovered, once the helium is restored, and once the energy is replaced in the magnet, the system will come back to life. Quenches are recoverable. We all build our magnets to survive quenches. Very, very rare cases. I've had one in my entire career where the magnet was not recoverable. So yes, they are designed to survive a quench.
Okay, there's one more question about who is responsible for routine maintenance, calibrations, and checks, whether being the biomedical engineer department or the imaging department officer. I think I will leave the stage to Edna and Jim later, but I think you have to look up in your state regulation, in your country regulation, sorry, because they vary from one place to another. For example, in Italy has been changed lately, and biomedical engineers can be in charge of maintenance, calibrations, and checks. Yes. And responsibility for an MRI site. I don't know. I'm not aware of what's going on throughout the world. So maybe Edna and Jim can fill up with that.
That is the same in areas where I am familiar with, certainly in the United States, other areas where GE operates. As a training function, I do train customer engineers. I train third-party engineers, just like I train my own field engineers. So it is done. Okay. It's a facility decision.
2 more questions.
It can be done by clinical engineers or field engineers of the companies. Here is the most common situation, most common case.
Okay. 2 more questions for you. We'll start with you, Edna, and then maybe Jim can fill in if he feels like it. There are 2 questions. One is about the problem of dealing with MRIs in the operating room. So which type of care should be taken? And the other, which is a long time question, I've heard that many times, and I don't have the answer myself, whether it's a 1.5T or a 3T would be preferred for pediatric patients. So Edna, if you start first, and then maybe Jim will fill in later.
Okay, so the higher intensity magnetic fields tend to allow us images with higher contrast and even high spatial resolution, depending on the case. So I think that 3T is the better choice if you can have it.
I would tend to agree, but again, it's a clinical decision. Some imaging on a pediatric case may be more appropriate at 1.5. but things are more visualized at 3, so it depends on what the physician is looking for.
Okay, 2 more questions that kind of go together. One is, what is the most common source for a quench? And the other is whether an abrupt shutdown and the power loss of the grid may pose threat to the equipment.
Did I completely answer the first question, Umberto?
Yes, I think so.
Okay.
There's, yeah, okay, just go ahead with the common source for quench.
Yeah, most common source is usually by my hand. So it's the process of putting energy into a magnet is very dynamic and prone to quench, as well as taking energy out. Once the magnet is stable at its field and it is in a stable operation, quenches are quite rare. And the most common quench, again, would be something called spontaneous, where the magnet just releases its energy because it wants to, followed closely behind initiated quenches by an operator due to a safety incident.
Okay, and the other one is about the power loss on the grid. As far as I know, is more the part that are more concerned with the power loss of the grid are the PCs and then the electronics of the device rather than the magnet. Sure. But Jim, I guess
that is generally true. There's a buffer time between or a parameter we call ride through. Because there is a reserve of liquid helium in the magnet, loss of the cooling systems does not immediately result in a quench. So losing the cooling systems in a power outage condition accelerates the rate by which helium evaporates and is vented out of the magnet. And only after the magnet liquid level drops to a critical point that the magnet can no longer maintain its superconductivity, then it does shut down. Those, depending on magnet product, can be measured between 7, 10, 12 days, depending on the initial condition of what the level was at the time of the blackout.
Okay, one last question is about the topics to be discussed between the vendor and the architect during the kickoff meeting for the site planning. I would say myself, just trying to figure out if you have enough space and to put all the devices and enough space for the patient room and the magnet room. Plus, I would rather be really looking into air conditioning and cold water supply to have the cooling of the system. But Edna and Jane can fill in.
Yeah, every one of us as an OEM, we document an introduction to our product. It's called a pre-installation manual, things a facility would need to concern themselves with before considering siting our product. That would be the first place to start. They're all in a logical order: major infrastructure, minor infrastructure, delivery routes. All of those requirements are in the pre-installation guide, and we all publish them.
One is about, just out of curiosity, if there are MRIs that do not use helium technology. I'm not aware of, but you know better than I do.
Yeah, so there are a field of superconductors called high temperature superconductors, alloys other than niobium titanium, that do exist, but they've not held up well to be practical at higher fields. There are some practical natures about their physics that don't allow them to operate in high magnetic fields. So we haven't gotten away from helium yet, but some OEMs have created minimal helium cryostats, meaning a few dozen liters of helium is all that's required to maintain that state of superconductivity. The challenge then becomes for those products is the dependency upon the cooling systems is much more elevated because you don't have the buffer of a large volume of liquid to account for a power outage or a lack of cooling condition. So like everything else, nothing comes free. There is a trade-off.
Okay, 2 more minutes to go.
Certainly.
Edna, what advice is put in place for patients with pacemakers requiring MRIs?
So there are some kind of pacemakers that are compatible with MRI scanners, but it's not the common condition, right? So if the patient has a common pacemaker, they will have to do a CT scan or other exam technique.
Okay, and one last question to go. Which one is ideal or more effective in terms of maintenance being conducted by a medical engineer and a clinical technician? I would rather say there are mainly differences. I mean, if clinical technicians is the one conducting the exam, I think he should be worrying about clinical issues and stuff like that. Although it might be a matter of training if the expertise and how far you can go into maintenance. As clinical engineers, we're stating basically that we have the competencies and the training and the expertise to do the maintenance. I don't know if Edna and Jim agree with what I just said.
It has been my experience that the clinician, the person sitting at the console, the person required or responsible for patient care, screening, safe operation, acquiring the image that the physician has asked for, typically focuses their effort there. However, those folks can be great conduits of information to the clinical engineering team of what they've seen, what they noticed, how did the failure happen, and the clinical engineer's edge on everybody is you're right there in the building. So first response, time to on scene, being a part of the problem, that collaboration cannot be beat.
Okay, we're done. We're running out of time. There's one more questions about the opportunity of acquiring MRIs from a donor agency across the world. I think there are. There might be cost or cost-free, but as far as I know, probably there's only a few people who'd rather delocate an MRI device in a growing country, as we call it. Basically because, as you saw throughout this webinar, it's kind of a complex environment and complex installation. So it can be done, of course, but you need to provide all the availability of to have the system run correctly. Otherwise, it might end up in lower safety for patients and lower level of quality of the image and healthcare itself. So we're finished with the webinar. I'm really glad to have had you here for this hour or so. As Kaliroy is showing, our next webinar from the Global Clinical Engineering Alliance will be end of November 9th at 7 p.m. Universal Time, and it will be regarding imaging equipment, especially CT scans. So we're keeping up with these technology updates, and I hope you'll join us also for our next webinar in less than 2 or 3 weeks. And thanks a lot. Hope to see you soon, and we'll keep in touch.